Suppose we have the sketch of a graph of some function. Here's part of a sketch of a function just for x values from -4 to 4 to keep things simple to begin with. Now what this function may be, I really don't know. And we won't really need to know that for what we're going to look at. What we're going to be interested in is some patterns here, so develop some rules for what the graph of a very closely associated function would look like. The kind of question we're going to be interested in is this. If we know what the graph of y equals f of x looks like, then what would the graph of y equals f of x minus c look like, where c is some constant? Well, let's go back to our example, and rather than do it completely abstractly like this, let's choose a particular value of c, say c is 3. So here is our original function sketch, and what are we interested in doing? We are interested in drawing the sketch of y is equal to f of x minus 3. So let's see if we can see where to draw some of the points on our new curve. Our original curve starts at a value of x of -4. Can we work out what the value of y would be on our new curve? We would have to know what the f of -4 subtract 3 is. Or -4 subtract 3 is -7. What was f of -7? I have no idea, because there is no part of the curve drawn above that point, so I can't plot a point above -4 for our new curve. Similarly, the same thing for -3. That would involve finding what was plotted on the original curve above -6, which is nothing. Similarly, for -2, that would involve finding what was on the original curve above -5, which is nothing. But when it comes to plotting a point above -1, I would have to investigate f of -1 subtract 3. Oh, that's f of -4. And I do have a point on the original curve plotted above -4. There it is. That would be the point -4, 5. So now I know what to plot above -1 on the new curve. It's the value of y when on the original curve we had an x of -4, and that value is 5. So I plot -1, 5. So we have our first point on our new curve. Now what would I plot above an x of 0? Well, that would involve checking out what f of 0 subtract 3, or f of -3. I've got a value for that as well. That's the value of y, 2, which I would have to plot above the x-coordinate of 0 on the new curve. Now I can continue this process. Every time I move along to another point, I would have to look at where the old curve was 3 units to the left. Right, am I finished? The original curve only went up to an x of 4. But we don't have to stop here, because if I want to know what point on the new curve I should plot above x equals 5, I'd have to find what f of 5 subtract 3 is. That's 2. What was f of 2? Oh, there is a value. Look, it's a y of -1. So when I have an x of 5, the point on the new curve will be 5, -1. And I can continue this also to an x of 6 and an x of 7. But then I do have to stop, because if I try to work out what to plot above an x of 8, that would involve working out what f of 8 subtract 3, what f of 5 is, and the original curve wasn't drawn at that point. Well, maybe now we can see what the entirety of this new curve is. Let's get rid of the coordinates on those points, just to declutter things a little bit. And now we can see that the curve that goes through all of those points is the same as the curve that we started off with, but moved 3 places to the right. This suggests that the answer to our original question is that if we know what the graph of y equals f of x looks like, then the graph of y equals f of x minus c would be the same as the original graph, but translated c units to the right. So let's go back to our example, and this time we'll do it for f of x minus c rather than f of x minus 3. And we have the ability to actually change the value of c. Let's put it back to 0. So in that case, the two curves will coincide. And let's see what happens as we increase c from 0, say, to 5. Well, as c increases, the curve does indeed move c places to the right. And if c now goes back to 0, so the curves coincide, and then we let c become negative, it moves c places to the left. But there again, if c is negative, then really we have moved c places to the right still. It's just that that is a negative amount of movement to the right, and therefore that is movement to the left. Our general rule seems to have worked out fine. So let's see a formalized way of writing that up. Here then is our first transformation rule. If we take a function and we replace x with x minus c, that's the algebraic change that we make, then the transformation we do to the graph is to translate it by c0. This is a better way of describing translations than just talking about directions left, right, up, down. If we say it's a translation by c0, written as what we call a column vector, with one number above and one below, that means that we have translated it c units in the x direction and no units in the y direction. It has not moved up or down at all. A similar question to the one we've already looked at would be to ask, if we know what the graph of y equals f of x looks like, then what would the graph of y equals f of x plus c look like, where again c is some constant. So returning to our original curve, this time we're trying to answer the question, can we draw the graph of y equals f of x plus, and let's go for 2 this time. So, in the original curve, y equals f of x, we know that above negative 4 we would plot the value 5. What would we plot now? We would have the original value of f of x, which is 5, plus 2. So we would plot a y of 7 above that point. Let's just clarify that. If our original point on the curve above negative 4 is 4, 5, a value of 5, then our value on the new curve will be negative 4, 7. Similarly, if I want to know what to plot above negative 3, on the original curve f of negative 3 was 2, but now I'll have to add a 2 to that, giving me 4. If I keep moving along, you can see that I can work out the value of y equals f of x plus 2 for all of the same values that I could originally understand what y equals f of x was. So we can build up the points between x of negative 4 and 4 for the new curve, and now perhaps if we remove those 2 points to reduce some clutter a bit, and now try joining up all of our new points, we can see that the curve of y equals f of x plus 2 is the same as the original curve, but moved up 2 places. What will we now get then if we try and make this more general and again do it for y equals f of x plus c? Once again, we have the ability to see the value of the constant little c and vary it. Let's just remove all of our dots so that we can see things a bit more clearly. Well, as the value of c changes, the curve changes position in the vertical direction. It is always c units above the original curve. If c is negative, that means that it will be below the original curve. Again, this suggests that we have our general rule that if we know what the graph of y equals f of x looks like, then the graph of y equals f of x plus c is the same as the original curve, but moved up c units. Now, as you will see later, it is much more convenient if instead of talking about the new curve as y equals f of x plus c, if instead we subtract a c from both sides, so that the new curve is y minus c is f of x. Why is that better? It looks a bit more complicated. Well, if we write our conclusion like this instead, what has happened to the original curve? Everywhere we see a y, we've replaced it with y minus c. Then the graph transformation follows exactly the same form as what we had for our previous case. If you replace y by y minus c, you end up with a curve which has been translated by 0, c. In other words, it hasn't moved left or right at all, but it has moved c units up. Here's an example of an exam-style question about translations. The diagram shows a sketch of part of the curve with equation y equals f of x. The curve intersects the x-axis at A and C and has a minimum point at B. On the same diagram, we would have to sketch the curve with equations. Firstly, y equals f of x minus 5, and in the second case, y equals f of x minus 5. And we're asked to show the coordinates of the images of the points A, B and C on the sketches. That's a bit difficult to see that curve there. Let's go and inspect it more closely. So here is that curve. We can see the coordinates of A and C, where the curve intersects the x-axis, are negative 6, 0 and 9, 0. And the point B, which is a minimum point on the curve, is negative 1, negative 6. And we are asked to draw the curve y equals f of x minus 5. Let's just have a little think about what we think is going to happen before we see it on our graphics package. If we replace x by x minus 5, which is what we are being asked to do, that should be the same as translation of 5, 0. In other words, we think that the curve should move 5 units to the right. Let us bring up our new curve and the value of c. If c is 0, then the two curves will coincide. Let's increase c up to 5. Indeed, the curve does move 5 units to the right. And more than that, we can work out the images of A, B and C, images being where they end up after we've done the translation. The point A will move 5 units to the right. It will now be at negative 1, 0. We usually call the images A dashed, B dashed, C dashed. The image of B, if that moves 5 units to the right, it will now be at 4, negative 6. And C, if that moves 5 units to the right, that will now be at 14, 0. The second part of the question asks us to sketch y is f of x minus 5. So, if we have a curve y is f of x, and we want to see what happens when we change it to y is f of x minus 5, what have we replaced x by? It doesn't look like we replaced it with anything. But if I write this second form of the equation as y plus 5 is f of x, just moving the 5 to the other side, we can see that what we have done is we've replaced y by y plus 5. And you can write y plus 5 as y subtract negative 5. So therefore our translation rules say that the graph should be translated, we should have a translation of 0, negative 5. In other words, this time the graph should move down by 5 units. If we return to our graph and superimpose over the curve of y equals f of x, y equals f of x plus c, and we were interested in the graph of y equals f of x minus 5, so our value of c will have to go down to minus 5. If we take it down from 0, where they coincide, to minus 5, we do see indeed that the curve has gone down by 5 units. And if we look at the coordinates of where A, B and C have moved to, then in every case the y coordinate had 5 subtracted from it. Negative 6, 0 has moved to negative 6, negative 5. Negative 1, negative 6 has moved to negative 1, negative 11. 9, 0 has moved to 9, negative 5. As a final comment, it's worth noting that the way that I have described this is a little different from the way you will often see it described. Often the translation in the x direction is described as saying if you go from y is f of x to y equals f of x plus c in brackets, that's the same as the translation of negative c0, and that if you go from y equals f of x to y equals f of x plus c outside the bracket, then that's a translation of 0c. Now both of these are completely correct, and you should be able to see that this is the same effectively as the way that we have done it. In the first example, we have described this as changing x to x minus c, which is the same thing as x plus negative c, So that would mean our translation, instead of being negative C0, would be C0. So that's what we have said. In the second case, this is exactly the same as what we have said if you subtract the C from both sides and write it as instead a replacement of y by y minus c. Why would I recommend this alternative way of doing it to you? Because looked at in this way, we effectively have just one rule, which is very easy to remember, rather than two slightly different ones when you have to think, am I going plus c or minus c? In both cases, if you replace x or y by x minus c or y minus c, then you have a translation of C0 or 0C. The important thing to note is that the C in the top row is in the x direction because it's the x that's been replaced, and in the bottom row the translation of C is in the y direction because it's y that's been replaced. Although slightly trickier to get to grips with in the first instance, I recommend this way to you because I feel it will be easier to remember in the long run.